Good day, guys. Alright, so in this video, I want to talk about rotational dynamics. So when you go from kinematics to dynamics, you have a lot more physical consideration to take into account. So, for example, in this particular video, we'll take into account the moment of inertia, right? So, um, a moment of inertia is, as an introduction, it's analogous to mass. However, it is related to the distance of one particular particle from the center of rotation as well. So let's just look at the definition for moment of inertia. Okay, so there are two perspectives that I want to introduce to you. The first one being a mathematical definition, and the second one is physical. What I mean by mathematical is that we can produce an equation and it's quantitative. Whereas when I talk about physical, I mean something that is physical in a sense that you can sense it, okay? And not necessarily in an equation form, all right? So mathematically, how do we define moment of inertia? It is defined by the sum of the product. So sum of the products of mass of each particle and the square of its respective distance from the rotation axis. So let's just call that respective distance to be r, and we have to square it, right? And that is our moment of inertia. Okay, so here's our equation. Whereas for a more qualitative description, the moment of inertia is a quantity expressing the body's tendency to resist. It resists angular acceleration. So when we say a body has quite a high moment of inertia or large moment of inertia, what we mean by that is actually that it is very prone to um, resist angular acceleration. Okay, all right. So let's look at the some examples, right? Some examples depending on the shape or the position of the axis of rotation. All right, so let's look at the first one, right? The first one here, we have a rod and we have the axis of rotation. So axis of rotation at the center of that rod, and the length of the rod is L, and what we have is the moment of inertia is equals to 1/12 multiplied with the mass of the rod and the squared of the length of the rod. Okay, now this is the moment of inertia of that rod. That is how much it would take or how much it would resist for it to undergo angular acceleration when it moves, when it rotates that way. Okay, now if we shift this rotation axis of rotation to one end, right, the moment of inertia also changes, because now the tendency, if you push it here, right, you will need a lower force. Wait, no, sorry, a higher force, okay, to rotate it. So it has a higher tendency to it has a higher tendency to rotate about the axis of rotation here. All right, so again we have m as the mass of the rod and L as the length of the rod from one end to the other end. Okay, so here we can see that the positioning of the axis of rotation also comes into play in the consideration of the equation for moment of inertia. All right, and then of course the last one, the very typical example where I would give you the moment of the equation for the moment inertia of a sphere, which is just 2/5 times mass of the total sphere, and the r, which is the radius, right? The radius of that sphere. Okay, so that's a very simple case, but of course this is not a list of equations for moment of inertia. You can always look it up on, for example, Wikipedia for those equations or any other statics textbook. All right, okay, so now I want to reintroduce torque. All right, we've learned about torque before, right, in the previous video where I defined torque to be the cross product between R and F. Okay. Now what I want to do is I want to relate torque to moment of inertia. So torque to moment inertia and angular acceleration. Okay, and how we do that is we look at the kinematic analogous, which is force. So according to Newton's second law, we have F equals to ma. And since moment of inertia is analogous to m, right, and the angular acceleration is analogous to linear acceleration, and torque is actually analogous to force, then we can quite correctly assume that the torque is going to be equal to I multiplied with alpha. And that is how you calculate or you get the equation for torque as a function of its moment of inertia and the angular acceleration. Okay, that is all. That marks the end of this video. All right. Again, I presented to you two definitions for the moment of inertia. I have given you three examples of cases or shapes and their equation for moment of inertia, and then we've revisited torque, right? Where instead of talking about the distance and the distance and the force that is applied, we talked about torque as a function of the moment of inertia and the angular acceleration. And again, let me just remind you that this is analogous to F equals to ma. Alright, so that is all for this video. I'll see you in the next one. Thank you very much.